So we left off on looking at this is like the exact example we did on our way out the door. Okay. The person in class clearly pointed to one while saying that one. So I can figure that one out, right? So the one that has a smaller group beside the carbon that has the leaving group on it or has the halide is going to be faster, right? So a big group is going to block the nucleophile, right? It's not going to let you specifically SN2 nucleophile minus. It's going to make it harder to get to that carbon that has your halide on it. What if we had actually like use letters. There we go. To make words. B would be faster. Right? It's easier to get to, again, the carbon that has your halide, right? It's easier to get to this carbon. And B, because it only has 2 methyl groups beside it, as opposed to in A where you have 4 methyl groups. BB faster, yeah, that's right. BB8, BB faster, whatever, man. B is. There you go, faster. All right. So, all right. And the last thing is something we've talked about, right, is the inversion of stereochemistry. So how does stereochemistry get inverted? Right. So we're gonna just do like kind of the simplest possible SN2 reaction, right? Where we're gonna have a nucleophile, add the like methyl bromide, right? So if we think about our carbon, right, you're gonna have, it's gonna be tetrahedral, right? And your nucleophile has to sneak up on the carbon that has the leaving group on it. And when it does, what happens is, again, just like every other reaction, right? It's not like the nucleophile adds and instantaneously knocks off the halide, right? We draw it like that, but there is a transition state. So the transition state of an SN2 reaction is where you're starting to make the nucleophile carbon bond, and you're starting to break, in this case, the carbon bromine bond, right? So those are partial bonds, right? The nucleophile is starting to interact with the carbon to make the carbon nucleophile bond, and that's causing the bromine to start to take its electrons and leave, right? What that does to the hydrogens is your hydrogens, basically you blow the carbon inside out. So as you're making the bond, your hydrogens go from kind of being cupped back like this to all in the same plane, right? And then at the end of the reaction, you have turned your chiral carbon, your chiral center, all the way inside out, right? So instead of being kind of like forward and to the left, the hydrogen is now forward and to the right. So it's like this to this to that, like Naruto run. You end at Naruto run. Right? Like when, like, remember last year, the biggest thing in our life was when we had to like Naruto run at area 50, at area 57 or whatever. What's area 61? 51. God, I know, it should be better than that. Right? And there's the greatest meme ever is, or the GIF ever is the guy like reporting and just one kid runs by him Naruto style. That was the biggest thing that happened last year. This year, it's like, oh man, like if someone Naruto ran at you, you'd be like, they have the coronavirus, and you'd run away. It'd be awful, right? So you're blowing your carbon inside out. So as you add, you kind of push all the groups from one side of your carbon to the other, and it inverts your stereochemistry, right? Your bromine is on the right-hand side, right? And then you turn your carbon inside out, so now your nucleophile is on the left-hand side, right? And that's why your stereochemistry inverts, is because you switch what side your big group is on. Now here I don't have stereochemistry, but it's way easier than trying to draw a bunch of methyl groups and turn it inside out. That's what happens during the reaction is you add, you start to make your bond, start to break your bond. When you make your bond, all your hydrogens end up on the other side of the carbon. Another way to think of it is like if you had like an umbrella and you were in like a bad sitcom, right? The wind blows, your umbrella's this way, the wind blows, and it blows inside out. That's basically what you're doing here, right? You've got all your hydrogens on one side, and then it gets blown inside out, and it flips the other way. And that's what's happening, is your nucleophile is flipping your carbon the other way. So what are things that kind of play a role in our SN2 reactions? So what is going to impact the rate beyond, if it's primary, secondary, tertiary, right? So first is the type of leaving group. / halide. Right. For us, our leaving groups are going to be almost exclusively halides. Right. So right. So the weaker the base that you generate, the better that leaving group is going to be. Right. So there's the things that make unreactive anions, right? You spit your leaving group out of your molecule, you make an anion, and if that anion is not super reactive, if it's stable, that thing is a good leaving group. So, all right, let's say we have X, we have our nucleophile. Right, so we're talking about this X, the thing that comes off the molecule. You want that to be a weak base. So for halides, our leaving group ability So iodide, or you can leave it as I minus, right? This is our best leaving group. This is our fastest reaction. So when you have iodide as your leaving group, that's when the reaction is the fastest. Because I minus is the weakest base that you're going to make of your halides. Then you have bromine. Then you have chloride, which is a big gap, super big gap. Then you have fluorine. So for kind of like, to give you like a sense of scale, if we set the rate for fluorine to 1, the rate of an SN2 reaction with iodide is 30,000 times faster. The difference between fluorine and chlorine is a factor of 200. The difference between bromine and chlorine is, I got to do math in my head, carry it to 2, it's a factor of 50. It's like 1, 200, 10,000, 30,000, right? So as you go, as these get bigger, they become better leaving groups, right? Because they are weaker bases, right? Bigger anions are weaker bases. So you have, say, I minus versus F minus, right? Iodine starts with a bajillion electrons, right? However many, like 80, 90, whatever, a bunch, right? I should probably know that, but I don't, right? Fluorine has 9 when it starts, right? If you give iodide an extra electron, it doesn't really notice, right? It goes to from a bajillion to a bajillion plus 1. It's like, whatever, who cares? Fluorine goes from 9 to 10, right? So now fluorine's way more negative than it was before, and it really notices that 1 extra electron, so it wants to go do something with it. It wants to go be a base, grab a proton, do something. Where iodide's like, is there an extra electron out there? I used to use Octomom as the example, but she's kind of getting it as a dated reference. Exactly. Octomom, there was a woman like 25 years ago who had literally 8 kids at once. Like, I guess now, like the Duggars, you know who the Duggars are, right? The Duggars are iodide. If an extra kid showed up at the Duggars house, they'd give it a hot dog and a bath. They would be like, I guess this is one of ours. I don't know, right? I'm fluorine. I have 1 kid. If a second kid showed up, I would notice. And I'd be like, yo, you're not mine. Why are you here? You've like really increased my workload by 50%. If you're on the Duggar compound, it's like we've got like 85 kids. What's the 86th kid? Who cares? Like, I guess we'll put a little shirt on here with a number and we'll just be good. Right? That's iodide. It's like, oh, an extra electron? Pfft, who cares? No big deal. I don't mind having an extra electron. Right? So these bigger anions are just better able to stabilize that negative charge because they're so big they don't really notice that they have an extra electron, right? That extra electron kind of gets lost with all the other ones. Where when you're small, that negative charge is more pronounced and is more strong, right? You have something that is much smaller that has the same charge, it's going to be more reactive, right? So as we increase size of our leaving groups, they get better, right? So if you remember, it's fluorine, chlorine, bromine, iodide, small to large. So as we go down, right, our leaving group ability follows our size for the most part. So we have our leaving group. We know typically the bigger the thing, the less basic it's going to be. Right? And then the other thing we have to worry about are nucleophiles. Right? In our kind of our shorthand here is strong bases make strong nucleophiles. So if something is a good base, it is going to be a good nucleophile. So what I want to do real quick is just kind of talk about the difference between a base and a nucleophile. Because what we're going to see as we go forward is bases and nucleophiles have the same structures. So like hydroxide, it's a base, but it also acts as a nucleophile. Right? So kind of the definition difference between them is, right, bases share electrons with hydrogens, right, remove H plus, right? They remove H plus from a molecule, where nucleophiles attack an electron poor carbon to make a nucleophile carbon bond, right? And with a base, you end up with a nucleophile hydrogen bond, or base, I should say, a base hydrogen bond in the end. And with a nucleophile, you're not attacking a hydrogen, you're not grabbing an H plus, you're attacking an electron poor carbon. And so depending on the reaction conditions, your hydroxide will sometimes act as a base, right? Or it will act as a nucleophile. So for right now, until we get to the elimination slides, hydroxide is going to be a nucleophile. When we get to the elimination slides, I'm going to teach you what reaction conditions favor it being a nucleophile and what reaction conditions favor it being a base, right? So there are certain things you can change about your reaction that can make the hydroxide be a base in some cases and a nucleophile in others. For right now, It's going to be a nucleophile. So it's just going to add to electron deficient carbons. All right. So kind of our examples of our strong bases that are good nucleophiles. Right. Stuff like hydroxide. Alkoxides. So I have methyl, but that could be any carbon group, ethyl, propyl, whatever. Negatively charged nitrogens. All right, these are strong bases that are also good nucleophiles. All right. And then we have weak bases that are poor nucleophiles. Right, things like water, alcohol, ammonia, and amines. Right, the big difference, right, is our strong bases, good nucleophiles. These are all charged, right? They all have a charge, makes them a strong base and a good nucleophile. The weaker ones are uncharged. They still are able to be a base or be a nucleophile, but they don't have that charge. They're not nearly as reactive. So far, so good? Okay. So a thing that we've not had to deal with up until this point is how solvent, how the stuff that you dissolve your molecules in impacts the reaction. And substitution reactions are the first time that we see that solvent can really play a role in how our reactions work. So if we look at nucleophiles, so if you have nucleophiles that are the same size or similar sizes, they're not going to be impacted by solvent. Solvent only matters when your nucleophiles are different size. So I don't know why I turned the oxygen one around. Oops. Increasing. Nucleophilicity. Right. These are all the same size, or roughly the same size, right? F minus, O minus, N minus, and C minus are all roughly the same size, right? So regardless of solvent, as you become less electronegative, you become more reactive. You're a better nucleophile. And that makes sense, right? Fluorine's the most electronegative element. It's the element that most wants to have extra electrons. So it's happiest when it has, of these, it's the happiest when it has an extra electron. Oxygen is the second most electronegative element. So it's pretty happy when it has an extra electron. The nitrogen and carbon are less electronegative, so they want extra electrons the least, right? So carbon is the least electronegative element of this group, so it has an extra electron. It's like, I'm not supposed to have this. I need to give this to someone. I need to go react with someone to give them this electron. Where fluorine's like, cool, I have an extra electron. I like having extra electrons. Right? So these are all the same size, but they're different electronegativities. So now when you have different types of solvents, size matters. Or when you change the size, it changes the nucleophilicity. So let's make sure. Right, so we have polar aprotic solvents. So aprotic just means that you do not have hydrogens in your solvent that are available for hydrogen bonding. So the molecule is polar, but it has no hydrogens for hydrogen bonding. Do you guys remember what you have to have when a hydrogen is available to do hydrogen bonding? There are like 3 types of hydrogens. So to hydrogen bond, you have to have an OH, right? An oxygen hydrogen, the hydrogen on an alcohol or a carboxylic acid, that hydrogen is able to hydrogen bond. There's an NH, so on an amine or an amide, or you just have the molecule HF, right? So for us, basically, a polar aprotic solvent has no OHs in it and has no NHs in it. In a polar aprotic solvent, small ions are more nucleophilic. So this means, so the easiest thing to do for these is to just go down the halides, right? And say, hey, these halides can be nucleophiles. So in polar aprotic solvents, fluorine is the best nucleophile. Then you have chlorine, then bromine, then iodide. I don't know why one got nucleophile, one got written out, but whatever. Right. So polar aprotic solvents do not interact with the nucleophiles. So if you think about this, fluorine is the smallest and it has the same charge as iodide, which is the biggest. So fluorine has the densest negative charge on it. It is the most negative of these ions. So it's the one that's going to be able to react fastest because it's the most negative, right? Where iodide has the same charge, but that charge is spread out over a much bigger area, right? So the smaller you are, the more concentrated your negative charge is, so the more reactive that negative charge is going to be. So what are some examples of polar aprotic solvents? right? So you have things like THF, acetone, acetonitrile, DMF, insert joke about South Carolina resident DMX here. But see, no one knows who DMX is anymore. No one remembers early 2000s rap. He used to bark a lot. It was just his thing. Now he lives in like Greenville. People were like, oh yeah, I totally saw him at like the Food Line. And I'm like, interesting. All right. And then DMSO. Right. So these are all polar molecules that do not have an NH or an OH to hydrogen bond. All right. DMSO, back when I was your age, right, we had like the late night infomercials. It's like, and there's always some guy that was like, the cures I don't want you to know about. Now that's just like a website, or like, you've gone too many clicks down the rabbit hole on YouTube, and you're like on the Epstein didn't kill himself video, and then this is a video that comes up, is like, oh hey, if you rub DMSO on yourself, it'll cure cancer. And it's like, no, don't do that. It's a bad idea. DMSO, its claim to fame is it will carry anything dissolved in DMSO through your skin. So there's an experiment where you take like pepper and you put like just black pepper and DMSO, shake it up, and you put a drop of it on your toe, and you taste pepper in your mouth because it pulls all those chemicals into your body. So don't just randomly rub DMSO on yourself. Don't do it. It's used for werewolves. So these are your polar aprotic solvents. The other type of solvent are polar protic solvents. So, and protic means it has a hydrogen to make a hydrogen bond. So, big picture, these are alcohols, amines, say primary, secondary amines, carboxylic acids, and amides. Right. Mainly, though, alcohols and amines. We can have acids, or we can have, amides, primary or secondary amides. Right. Tertiary amines and tertiary amides, they don't have hydrogens on their nitrogens anymore. So it's only primary and secondary amines. So these are our polar protic solvents. Here, size matters. Okay, so the size of our nucleophiles matter in polar protic solvents. Insert jokes here. I'm not getting fired today. All right. So the bigger the ion, the better the nucleophile. right? So this is the exact opposite of polar aprotic solvents. So here, I minus is the best nucleophile. Then bromine, then chlorine, then fluorine. Right. And that is because polar protic solvents interact with the nucleophile. So polar aprotic solvents don't really interact with your nucleophiles, but polar protic solvents do. So we have I minus, and then we're going to have fluorine. Okay. What happens with a polar protic solvent is all those hydrogens, right, are slightly positive. So when you have an alcohol, the alcohol is slightly negative, the hydrogen is slightly positive. So what happens is all those hydrogens on your alcohol will hydrogen bond, will basically wrap themselves around the ion. So it's like, oh, hey, I want to put my positive atom near this negative atom, and I'm going to get all these like hydrogen bonds, right? So you've got this big iodide. Maybe you can get some solvent around it, right, and envelop the iodide. But it's really hard to cover the entire surface of the iodide, right? Because it's a lot bigger. Fluorine's smaller, so it's way easier to cover more of the area of your fluorine with solvent, right? There's less of your fluorine that's available because it's got, even has the same amount of solvent around it, the fluorine's just smaller, right? So it is easier for solvent to cover small ions. So basically what happens is when you're a smaller nucleophile or a smaller ion, solvent will completely and totally envelop that smaller ion, right? So instead of just having a bare F minus, you've got this F minus that's basically bubble wrapped in solvent. So it can't get to anything. Its negative charge is hidden by a bunch of solvent. Where when you have something bigger, right, it takes more bubble wrap. It takes more solvent to cover it. And so it becomes harder for the solvent to wrap itself all the way around that bigger ion. So more of the negative charge of that bigger ion is exposed and is able to get to a carbon to add to it. So in polar aprotic solvents, they don't interact. So it's just like, hey, which is the greatest charge density? Which of the ions is most negative? In polar protic solvents, the protic solvent tries to wrap itself around the ion, and it's easier to wrap yourself around something small than it is to wrap yourself around something big, right? So it tries to cover up the big thing, but it can't. So that bigger ion still has negative charge that's exposed and can get to the carbon that's positive. Where the small ion just kind of gets like wrapped up and then, is bubble wrapped. It's like a little bubble boy. It tries to like react and just bounces. It's like decent Jake Gyllenhaal movie, Bubble Boy, but whatever. Okay. So what are some like actual examples of reactions, right? Things that are actually going to go on. So, right. So you can have hydroxide as your nucleophile, and you're going to displace your leaving group, in this case, a chlorine, and replace it with an OH, and you're going to make lithium chloride, right? So you can break this in half and say, hey, the oxygen is negative, the lithium is positive, so the negative thing is going to add to the carbon that has the leaving group on it. We can use sulfur. Again, sulfur minus, sodium plus. You can think of sulfur as oxygen's fat, smelly cousin. It basically does all the same stuff, but doesn't take a bath and just smells bad. Now, I'm going to show you kind of one example, lithium hydroxide. But it doesn't have to be lithium hydroxide. It could be sodium hydroxide, potassium hydroxide, right? You just need some metal to balance out the O minus. So, because I have NaSH, Nash. Don't think, oh, it always has to be that, right? It could be a potassium. It could be a lithium. So don't get locked in. And I'm showing you here the salt that you make, lithium chloride, right? That's what happens to the lithium that's on the nucleophile and the halide that's your leaving group. But normally you don't have to show me that on a test or something. It goes to the, if it's water soluble, I don't care. But I'm just trying to make sure that you can see where everything goes in these examples. As we do more, we're not going to care about it as much. Right? We can have also same with the halide. I'm just kind of cycling through all of them, but don't get locked into oh, lithium hydroxide only reacts with a chloride. Again, it could be anything. So I could have, right, alkoxide, R or OR minus. So again, metal plus, oxygen minus. I'm going to make an ether and potassium iodide. Again, if I can do it with oxygen, I can probably do it with sulfur. So I can have sulfur with some carbon chain on it, same deal, plus, minus, sulfur displaces the bromine, plus lithium bromide. You can do this with amines, right? Amines can be your nucleophiles. I know that NaNH2 was a base, at the end of alkenes or alkynes. We're going to use it as a nucleophile here, and later on I'm going to tell you how you differentiate the two. Right? You could also have, again, different groups, right? It could be lithium, right? You could have a carbon chain on your nitrogen. And again, we're going to add that. So I should be pointing out, right? So this carbon right here that had the halogen is that carbon right there. This carbon right here is this carbon right here. Right, so you're just knocking off the halide and putting whatever you've identified as your nucleophile in its place. Right, one that you know already is if you have an acetylide, right? Your acetylide is a nucleophile, right? That's how you built carbon chains, right? For synthesis, I'm gonna leave it the same way. Sorry. Great, this carbon here is that carbon there. Right, or we can use cyanide, CN. So here, the carbon is the nucleophile. So you're going to make a new carbon. Oops, I forgot my lithium iodide up here. Sodium iodide. So these are kind of like all just like, these are most of the nucleophiles that we're going to see for stuff. I think the only other nucleophile that we might see or that I usually use is some sort of acetate where it's O minus as part of like where you have a C double bond O. I want to just get this in here before we go, which is SN2 reactions prefer to be run in polar aprotic solvents. So if given a choice between a polar protic solvent and a polar aprotic solvent, SN2 reactions prefer polar aprotic solvents. So I'll touch on that a little bit more, I think, before on Friday, but you should be in a position now that you can watch the video. And then we'll kind of clean up the last little bit of this and then go on to eliminations. We'll like touch on some stuff from the video. We'll do a bunch of examples before we go on, and then to make sure everyone's like on the same page from the video, and then we'll do eliminations. So with that, it is 9:50 somehow.